And then we'll dive into the fun part, which is the implementation, preparing the data, training our model, evaluating the model. We'll do this with code and Visual Studio Code. So we start with our polyglot notebooks. If you don't know how to work with these, I have a video on it. Jupyter Notebook for C# and VSCode.net. Check that video out. And then we start by installing ml.net, using ml.net. Then we're modeling the input data. So this is the taxi trip, which I commented out some features. So these are the features, the inputs. Passenger count, trip time, trip distance, and then the label is the fare amount. So there's a separate class for that, taxi trip fare prediction. The training dataset. So, and then we can instantly see that we have about 1,048,500 records more. So that's a lot of data that we use to train on. Now we can preview this. And then you basically see the vendor ID, which is some kind of string, rate code, passenger count, trip time in seconds, trip distance, payment type, and the fare amount as the label. The rest are features. And I commented out the other ones since we need to do some different data transformations. So we can't really use string values, so we need to convert them to a representational value that could either be categorical, replace them to category 1 to 5, for example, in which, let's take the payment types, in which CRD is category 1, and CSH, which is likely cash and card, and it could be category 2, and so on. That's necessary since these algorithms can only deal with numerics, not with strings. Numerical representations, like let's say all these house prices, all these bedrooms, basically going to be used as an array, which we could call a vector or a tensor as well, a one-dimensional array. Okay, let's get started. We start by initializing an ML context with a seed, which is there to introduce some randomness during the training or the training data set, if I'm not mistaken, but we don't want to have it completely random. We kind of want to have it random each in the same manner, if that makes sense. Feel free to look up what this seed does. I have a basic ID. Anyway, we load the training data and the test data, which are two different sets. In this case, has header, so CSV and a comma separator. We'll load them as input data, so using the taxi trip input model. And then we're just gonna inspect the data. So we're gonna see what is the count of the amount of labels. And then we seem to, this is the Microsoft sample. And we filter the data to only get the fare amounts which are higher than 1 and lower than 150 to exclude anomalies, how we say, outliers, because that could skew the data. Outlier is basically, let's say we have a few historic points that are completely off. We don't want the model to skew to those exceptional data points. Okay, then we can, so these are all data views. Then we can preview them, either the column view or the row view, which is basically going to present us the values, but it only shows us the first 100. I think you can specify a limit. Maybe you only want to see 5. You can specify that in here. We're going to inspect the test data as well. Important is, of course, we want to have, let's see, we always want an equal amount of labels as features. Let's say there's a missing house prices or missing labels, then we'll have to fill that up with zeros. To have, let's say we have 10 values here, then we need 10 labels as well. Otherwise, that's not going to format well into the array, the vector as the inputs. Then step 2. So step 1 was load the data and inspect the data so things are fine. If there's some problems, in step 2 we can transform the data. Like I said, replace missing values or null values. Maybe we want to rename a column or drop a column, things like that. Transform, normalize, mean variance. That's just something I should explain later. And then we want to have a features column which has, well, basically we're concatenating all of these feature values into some kind of matrix or array or vector to then be used for the model. And then we made sure that the label values are under the label column. Because ML.NET wants to use label for the labels, well, you can specify it, but it's kind of a convention. And then features as for the X values, the feature values, the inputs. Then the trainer, you can choose your trainer by ML context.net regression.trainers. There's an option of a few different ones. You have SDCA, online gradient descent, you have light GBM, you have fast tree, and so on. Let's run the code so we don't have. What is missing from this, I think, would be nice to analyze the feature importance almost. We could visualize that and see if the data that we have is balanced, which means that the data is a bit like this. Not that all the data points are at the beginning and then we want to predict a data point at the end. That's not really balanced data. Or okay, then the data processing pipeline. Going to append the trainer to that. So what I wanted to show is trainers dot. I've got LBFGS Poisson regression of Poisson regression, online gradient descent, stochastic, something something, and got a few different possibilities. I think you should also have fast tree. No? Anyway. Oops. Then that wants the label column, so that could either be the taxi trip fare amount, the name of, so the string, or we called it label. We renamed it to label, and the features, the important feature values are concatenated into the features column as a vector. Number of iterations is how many times do you want the algorithm to train, so how many times is it going to look at the data, the training data set, and make predictions to minimize the error rate. You can kind of alter that. Then you can use the set, well, these values are kind of default, but you could play around with those, optimize its performance. Then, important step here, we specify a new variable and have the data process pipeline append the trainer. What I accidentally did, something like this. And that cost me 5 hours of trying to figure out why the training wasn't happening. So that's important. Then finally, we're going to fit the data to the algorithm, so to the learning algorithm. And that should, for 100 iterations, train the model. It can take some time. It's a good sign that it takes some time. If it's done instantly, something may have been wrong. So now we have a trained model. Print some metrics in which we find the R squared the easiest to interpret. So it's basically closer to 1 the better the model. It's basically like accuracy. Okay. Then you can evaluate on the test set. So if you saw, we have loaded the test set as well. The test set typically has less data. It's just used for showing the model after training and seeing how well it performs on that. So let's have a look. Test data is only still a lot of rows, 99,000, 100,000. It's not a million, so it could be like 10% of the data, which is normal. Sometimes you take 20%, sometimes we take 10%. The way I did that is you can also just split the training data. So what I do here as well is I shuffle the data. It could be important so it doesn't learn the chronology. Test split, there's a method for that, and then you can say the test fraction to be 0.2, it's like 20%, so you can make it 80-20 split, in which the train set then has 80% of the data, and the test set then has 20% of the data. And you see then the test set amount of rows here is 371, and here it's 1,500 almost. Anyway, this is a different example. Let's get back here. Now, since we have this trained model, we can actually use it for making predictions, but we don't really know how well it performs at this time. So we're going to do a simple evaluation on the unseen test data. This is, so now the model is going to do the same like it did with training. It's going to try to predict compare the predicted values to the actual values, so on the test set. And then that's those predictions. We pass that to the evaluation. We need to tell it the label column and the score column. This is a bit of an odd one. Basically, I think the model training adds this column, if I'm not mistaken. And then the label column is already given. Well, it should be present in the test data. Anyhow, the score is basically some like the newly predicted value, and this label should be the actual value. I hope that makes sense. So now we get the r squared is minus 0.1, which is terrible. As close to 1 as possible. So that's not going to do too well. Then we can consume the model. So we have that test data top. Well, some new unseen input data, which is this taxi trip, new one. And we just give it a passenger count and a trip distance, and we'll try to predict the fare amount on that. And I put the actual fare amount here just for logging. Actual one should be 29.5. Let's see what it predicts. I did it already. It predicted a fare of 8.1. Well, it should be closer to 29.5. So that's not that good. Below is some code I copied from the Visual Studio project. That's that to calculate those feature importances. But for that, it seems like we already need a trained model, which is a bit odd. So basically doing it after the fact and trying to see which features are most important, best related to the outcome, correlated. So now that our model was performing so badly, we can play around with, maybe we can add more features. Maybe one of these features is very important to predict the taxi fare price. Or we could start playing around with these hyperparameters. A number of iterations, we could maybe make to 500. Could adjust these settings. Or we could even try a different learning trainer, let's see. Want to do the light maximum. And then these are already kind of optional. But, let's try that. Now 500, that's going to take a while. Retrain? No? Oh, it's already done. Now we have an R squared of 59, almost 60%, so that should be way closer. So now it predicts a fair of 22.3, and it should be towards 30. That is already way better, so you can play around with all of these things. But it's possible that the data maybe is not as linear as we think. Maybe it's more complex. Let's touch up on a few more things. First would be, well, as you saw with the taxi fare prices, we didn't just have one feature, we had multiple features, which isn't represented by a single line, but rather something more complex. And then another thing that I skipped through was this, which we call feature engineering. These normalize mean variance. Let's see what it says. Normalizes based on the computed mean and variance of the data. There's a few different ways to do that. Well, normalizers, you've got a standard scalar, you've got a min-max scalar, and you've got this normalized mean variance. If I'm not mistaken, this one is bringing the values down. Instead of between 0 and infinity, it could be between 0 and 1. And this way, it kind of optimizes the training speed because the values are smaller. Because the more features you have, the more computationally heavy it becomes as well. Because what happens under the hood of these training processes is, let's say, sorry, these are the features. Oops. Could say we have, just gonna, for simplicity, bathrooms. It could also be property size, could be in times 1,000 or something. And what happens is all of these values kind of are formatted as a vector or like a multi-dimensional array, and with all of the numerical values in there. And if I'm not mistaken, these matrices get multiplied with each other. All kind of matrix calculations occur. And if you ever had this in school, takes quite some time to do this. For a computer, yeah, it's also quite heavy to do this. So yeah, so to make it a bit more efficient, let's say all these sizes were like, let's say it was like 20,000 square meters, 40,000 or 400,000, and this and that and that. With those scaling or normalization, you're basically gonna try to reduce those values to values between 0 and 1, smaller values. What sometimes happens if you have an image, we'll see that later, like an image, like a real image. Say this is an image, a PNG, and this has a resolution. Let's say it's 1024 on 1024 pixels. Then each pixel has a color value, which is 0 to 255, so from black to white. Then you may see that they are going to scale all of those values. So you basically have a huge matrix of 1024 by 1024 rows and columns. Then you need to start multiplying with that. It's quite heavy. So often they will reduce the resolution size, scale it down to like 100 times 100, for example. But then also maybe even remove the color values, make it just black and white image. And then those 0 to 255, they may scale those down to 0 to 1 values to make things more efficient. And also what the machine learning model learns, sometimes the color is not it doesn't have to be blue, it can be some kind of gray color. It can kind of reduce the quality, let's say, and it's still gonna learn the important patterns. Color and other elements can even just make things more complex or polluted. And then for different kind of values, like string values, we will turn those into categories, like I tried to explain. So we could use one-hot encoding for that. Maybe there's other techniques as well, but then basically you have the numerical representation of the category. So instead of, what was it with the payment type, instead of cash or card, you now have 0 or 1 or 1 or 2. But now the more features you have, the more complex the line, let's say, the function, the prediction function, the more complex the visualization actually, because as you remember, kind of each feature is kind of a new dimension. If I'm not mistaken, this would mean that if we add bathrooms, we would actually need to add an axis. So I just try to illustrate a third dimension, an axis for that. So let's just call it C. And then the formula is also going to be more complex. And then this function, instead of a straight line, become more like this maybe. And if you add another feature, let's say the size, you would add another dimension, and the function could maybe become more like, take another turn, illustrated well here. But yeah, the point would be to make a more complex function so we can fit the most data points. I hope you've seen this in school or something, or you take a in-depth course if you're interested after this, maybe in Python and more of the mathematical background. So I wanted to find a real applicable use case for my dog platform. And if you're not familiar, it's basically can put dogs in the spotlight, shelter dogs in the spotlight, and to increase their visibility and their chances on adoption. So my idea was, let's say a dog, we have historical data points of spotlights, dogs that have been in the spotlight, and we can use that as training data to predict the next time you put that dog or another dog in the spotlight, we could try to predict the amount of page views, extra page views, likes, swipes, contact requests, and you name it. Some metrics that I'm tracking, contact clicks, contact requests to maybe adopt them, maybe to promote them, put them in the spotlight. And we've got days in the spotlight. That's going to likely have a linear relation to the amount of page visits, I should hope. Page visit is actually a click through. So you see the dog on some kind of Tinder-like way, and then you can either swipe them, like them, dislike them, or click on it to go to the detail page. So that's basically a detail page visit. So the more spotlights, the more page visits should occur. Well, or the more swipes at least, because now the dogs in spotlights, they appear as the first dogs in the card deck. There's likely more relations that you could find in here. Days in the spotlight and spotlights count this fixed. Well, for now at least, one spotlight is going to put the dog in the spotlight for 2 days. So that's kind of always going to be, don't need to predict one based on the other, because it's just a fixed formula. It's times 2. Let's say I switched my spotlights, the amount of days, suddenly to 1, then you see that reflected in the data. Maybe that would be more of a use case for machine learning to predict its visibility based on a spotlight. But that taxi fare use case is a real one that I've seen. Some kind of Lyft driver tried it as well, which is kind of cool. But for these problems, there's so many variables. It could be the weather, the location, the season, the hour, the demographics. Okay, this is a similar but more general data set. It's not specifically for the spotlights. It's basically just the dogs, the age in months, so how old the dogs are, how long they've been visible on the platform, and then you could maybe kind of try to predict a popularity, perhaps based on the breed, on the gender, on the whether or not, well, how long it's been on here, and well, based on the likes, dislikes. Say we look at the dogs that have been in there the longest, they likely should have the most views, but they're not necessarily the most popular, otherwise they wouldn't be there anymore. And you could kind of play around. You could see maybe it's more of the larger dog breeds. Yeah, see the amount of dislikes, unfortunately, it's way higher than the likes. See the one with the most page visits and the most contact requests. And contact clicks even. Kind of an outlier, but still. It's been only on there for 12 days. Only 9 swipes, yet a lot of interest. Is already adopted, possibly. And that was a puppy Yorkshire Terrier, so a small doggy. Okay, anyway, so you could use this data to play around with it. So how you go about this is install the package, use the package ml.net, and then you load these columns. You need to make sure to target the correct column in the CSV. So this animal page visits, which is just named page visits in the CSV, it's at column 15, starts at 0, and then 18 you've got the promote button clicked. So I was gonna try to predict the amount of promote button clicks. So I would assume the more page views, the more chance they are going to put the dog into the spotlight. We've got this, well, this is basically the input data. So the input data, then the output data, original label and predicted label. We'll see that once we make predictions with the model. First things first, initialize the model. We pass a seed. We've got here 2 data sets to play around with that. The other one is even simpler, but it's just way too, it's not enough data. And I had to kind of group them by month just to separate them, to have multiple rows. This is basically a general amount of animal detail page visits per month in 2024, and then contact clicks, promote button clicks. So here you could try to predict the amount of promote button clicks based on the page visits. Same for contact, could try to predict that. And then maybe the actual conversion would be somebody paying to put the dog in the spotlight. Anyhow, we load the data. This time it's all in one data set. CSV, I did allow quoting because there's some quotes in there apparently. Need to make sure the data is not invalid. Fixes. Filter data column, so I don't want all the page visits that are 0, because that's maybe there's too many, and that's going to create to make the data unbalanced, and then it's more likely that the model will always predict 0 instead of a useful value, just because there is an overrepresentation of 0 values in there. So we're filtering that out, and then just having the row count, which is only 1861. Just some sample code. This time I'm shuffling the data, so it's not going to learn the order in which the training data is built. Well, train test split, so I'm going to have a train set of 80% of the data and a test set of 20% of the data. Just quickly going to preview what's inside the columns, the values, just to see if we have the correct ones. Okay, that's more like it. I messed up my data set because I took away a column, and now I had to make sure these indexes were correct. So now I have 1800, that's more like it. And let's go through the training. I'm shuffling the data, previewing the data, and then transforming the data just very simply. Copying the labels into the label column and concatenating the feature values into the features column. I add some more docs where you can get the code. Then trying online gradient descent, 100 iterations, or epochs they call it sometimes. And then you can get this, invalid values, and then infinite. And you can normally play around with those things, and then it suddenly does train. Then what we're doing here, preparing the test. So we trained, took 0.2 seconds. It's not that long. Let's try 500. 0.7 seconds. Because my data set is really small, it's only 2000 records instead of a million. Some more previewing. Then this is something I found in the docs. I'm basically the test data, trying it on the model, and then comparing the label with the predicted label, which is the results are quite bad. It's already first indication to see how well the model performs. And there's a major issue. They want the inputs and the outputs to be like of type single, which means like float or something, while the prediction should actually just be an integer. I'm kind of not happy with these double or float values as prediction. Should just be 1 or 2 or 3, an integer. Anyway, the metrics, and then we see a horrible metric, should be close to 1, but it's 0.04. Nothing to do with that. Then we try a prediction with 230 page visits. How many promote button clicks should we get for that? Then we get like 2.6 predictions for 200 page visits. Promote button clicks on the page visits. That is, let's see. So 517, but it's kind of an exception. Let's see. This times 10, 0. This times 10 would be 20-ish. Yeah, instead of 2. Yeah, it's not exact, of course. Anyhow, cross-validation, feel free to check that. That's basically evaluating the model in an iterative process. Then I added some more links to samples, and here the taxi fare prediction. If you likely can get the test and the training data there. I might not include that on my GitHub or on my Patreon because those files are too large. But let's reflect on why this model is so bad. My assumption is, well, first, only training with one feature, which is maybe not enough to really predict this outcome. Secondly, instead of 1 million records, I only have 4,000, of which I'm only using not even 2,000. Well, about 2,000. Yeah, that seems to be not enough. And then I could play around with these two, or maybe a different trainer. Let's see, can I do light BGM? No. Could try this, but could do even more iterations. Oops. Now it's gonna do that 1,000 times. The R squared seems a little bit better, from 0.02 to 0.08, if I'm not mistaken, but it's still not that good. Well, 12 could be more realistic. Anyhow, feel free to play around with that. As you may see, features like dog name is not gonna, well, it could impact the popularity. The name could impact that, but it's less measurable, I think, than maybe the breed. You could one-hot encode these breed things into variable categories. The shelter where they remain could also play a role in the adaptability or the popularity, and conclude that the model is not performing well, so we're underfit, what we call, which means that this function that this formula that we try to find or make is not fitting the data points well, or at least not performing well on new data points. So it could be all the way here or there or whatever. Doesn't have enough data to properly fit, or enough features. If I try this dataset, dataset 2, which only has like 10, 12 records, which is not enough data. But what could happen is it's such simple data that maybe the model just learns the exact data. Well, we try to prevent it by splitting test and training data sets. But let's say the model scores 100%, then we would say the model is overfit. It is the line would be perfect on maybe the few simple data points. And then it's likely not going to perform well on new data. Or maybe the relation between the data points has like a fixed formula where we don't really need machine learning. To regulate this overfitting and underfitting, we kind of play around with these hyperparameters. So you could increase the learning rate. If this is too large, you could, it's might take longer to find the local minimum. If it's too small, it could also take longer because it's kind of taking small steps towards finding the local minimum. This regularization could kind of steer the training, but do some self-study if this stuff interests you. I thought I was gonna be able to have proper predictions for this small data set. Unfortunately not. Why did I think that? Is because my most recent use cases with machine learning have mostly been using an already trained massive machine learning model, AI model, and then retraining it on a couple of hundred or thousand samples of custom data. So basically fine-tuning an already existing model, neural network, and that requires less data. But to train that same neural network from the start, maybe you need a crazy amount of data. And it needs to be quality data, it needs to be labeled correctly. So that's regression, simple linear regression, or with multiple features, more complex linear regression. Those same trainers algorithms you could also use for for ranking, basically in a search engine to try to rank the best results at the top. And maybe you use a vector database as well into the mix, and now you have a better understanding of how those things work. Scoring, ranking may be a topic for another video, but it's quite similar as regression, forecasting, prediction. You could add time series data to forecast on, which means you're not gonna train only on the point in time, the historic data point, but possibly also similar data points earlier or later, if I'm not mistaken. And you can predict instead of one value more of a sequence, like the weather for the next 7 days. Do like, subscribe if this was useful, to follow along for next episodes. To become a member, I'm going to drop the notebooks on there, not all of the data, but the code. And check out my Gisco.com product website